Okay. So here they say a 2 kg box is released from rest. And even if they didn't say rest, if they just say to you it's released, then you must know that initially it was not moving. The initial velocity was 0. So they say to us it's released from the point P, which is 5 meters above the ground. Okay, that's the height of the point P above the ground. Then they say it slides down a smooth, frictionless, curved track, which is PQ, as we can see in this diagram. And here they tell us that there is no friction on this track, on the curved surface, PQ. And when there is no friction, then you know that mechanical energy has to be conserved. Because every time there is no friction, there is no applied force, then we know that there is actually an isolated system. Okay. So looking at this system, yeah, the part PQ, we already talked about it. The only force that is acting on our box is the gravitational force. But if we look at the section QR, there is now friction because we can see that the surface is now rough. And they also tell us that from the point Q all the way to the point R, the distance is going to be 10 meters, which is also the displacement of the box. And then they say there's going to be a barrier at the point R. Of course, a barrier is anything that stops the motion of an object. So maybe it's going to stop when it strikes the barrier there. Then the first question says, state the principle of conservation of mechanical energy in warehousing. So yeah, it says the total mechanical energy in an isolated system is conserved or remains constant. That's fine. The next they say, use the principle of conservation of mechanical energy in order to calculate the speed of the box when it reaches the point Q. So yeah, they say we need to use the principle of conservation of mechanical energy in order to calculate the speed of the box when it reaches the point Q. And this is for 3 marks. Okay. It used to be 4 marks when you were back in grade 10, but of course, the older you grow, then the lower the marks have to be. So now the first thing we need to state is the principle of conservation of mechanical energy. It's what they said we should use anyway. So we tell them that the initial mechanical energy is equal to the final mechanical energy. But how do we define mechanical energy? Well, we actually know that it's the sum of the potential energy and the kinetic energy. And then, of course, we say this is equal to that. And this is what we say. All right. But now the question is, what is actually this potential energy? How do we calculate the potential energy? Well, we know that we take the mass multiplied by the gravitational acceleration. Then we multiply this by the height. Then we come for the kinetic energy. We say it's 1/2 m. And then we times this by v squared. So that's how we calculate the potential as well as the kinetic energy. And guess what? The first 2 steps are not really necessary. You can skip them. That's perfectly fine. Yeah, you can skip those first 2 and go straight to the third step. Okay. So now we need to come and say the mass of this box is 2 kg and the gravitational acceleration is 9.8. And initially, it was at a height of 5 meters above the ground. But for the initial kinetic energy, we can just say 0. Why? Because it was released from rest, which means the initial velocity was 0. So if the initial velocity was 0, then it means the entire kinetic energy is just going to be 0. Then we come to the right-hand side, the first part. The final potential energy is now going to be 0. Now the question is, why is it 0? It's because at the point Q, the height above the ground is now going to be 0. And if the height above the ground is 0, then the entire potential energy will die. So it's going to be 0 altogether. And now we can come and say, well, the mass is 2 kg. We are looking for the final velocity. Then these two will just cancel out. Half times 2 is 1. So on the right-hand side, we now have VF squared. And if you go to your calculator and say 19.6 times 5, well, you're simply going to get 98. And if you find the square root on both sides, then you find that your final velocity will be 9.90, and then you say meters per second, like that. So yes, there was no way you could have used the equations of motion in this case. Mechanical energy is the best way out if you are dealing with a curved surface or the work done by non-conservative forces. But since there is no friction applied force here, then it means there was no way you could have used the work done by non-conservative forces. Let's move. So the next statement says, the box passes the point Q and moves 10 meters on a rough horizontal surface before striking a barrier at the point R at a speed of 4 meters per second. Listen to that. Now they tell us the velocity at the point R, which is the final velocity, the velocity with which the box strikes the barrier. If you take it to vertical projectile motion, they used to say calculate the velocity with which the ball strikes the ground or hits the ground. Now, the velocity that we just calculated previously, the speed at point Q, it is the final velocity if we are dealing with the curved track, but it becomes the initial velocity when we are now dealing with the horizontal plane. Do you see that? So the initial velocity is 9.90 and the final velocity is 4 meters per second. And we also know the displacement. So the question says, use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. And of course, there's only one horizontal force acting on this box as it's moving between Q and R, and that is the frictional force. Now, you can actually do this one in one of two ways. You can use the work energy theorem Or you can use the work done by non-conservative force, even though there is no change in potential energy. But you can still use that formula as well. Even though there is no height, it's not really restricted to when there is a height. Okay. But let's go to the work energy theorem. It says every time when a net force acts on an object, the net work done on an object is equal to a change in its kinetic energy. And the reason why we pick this one, well, it's because they gave us the final velocity as well as the initial velocity. So definitely we know that there is a change in kinetic energy. But then the question is, what is your net force in this case? Well, it is actually the frictional force. What did they say anyway? They said we should calculate the magnitude of the frictional force. Okay. Which is our net force. Okay, sorry about that. So the question is, how do we calculate the net work anyway? Well, in order for us to calculate the net work, even if there is no electricity in your area, you just need to take the net force, multiply it by the displacement, and multiply it by the cosine of theta. Or you could have just decided to say, instead of you saying net force, you can say the kinetic frictional force, because you understand it is the net force in this case. But let's just keep the original formula. It's always nice if we deal with the originals. I remember there was a Facebook meme whereby there were two people sitting on a table. One of those two people was a Chinese, or maybe he looked Chinese or something, and he was wearing Adidas. And then he was talking to this other black man. Ne? Now he was pointing at the black man like this. He was saying this. Now someone wrote a caption and said, "Wa bona le Adidas e ke e rwetseng e? A re ke iketseditse yona." Yeah, no, I'm not sure if you understand what I mean by that, but nevertheless. Now, yesterday we learned that we don't need to say 1/2 mv squared minus 1/2 mvi squared. I wanted to say vf squared and vi squared. We learned that instead of that, we can just say we have 1/2 here, and then we say vf squared minus vi squared. Okay. Then now we can come and say, but we know that our net force is the frictional force, and our displacement here is 10 meters, and the angle has to be 180 degrees, because remember we said theta is the angle between the force and the displacement. So in this case, the displacement is going to the right, but the frictional force is jealous. So the force between the displacement and the frictional force is 180 degrees. I wanted to say the angle between those two, not the force. What am I saying? Now we come back and say, well, our mass is 2 kg. The final velocity is given to us as 4. The initial velocity is the one we calculated previously. So that's what it's going to be. And now we have negative 10 times the kinetic frictional force. And of course, this one is just going to give you 1. And here you have 16. So if you now go to your calculator and say 4 squared minus 9.90, or you could have used the 8.9 watt, the one that we got previously, right? Yes. So if you say 4 squared minus minus what? minus the square of that. Remember, before we found our VF, we once had VF squared, which was equal to, what was it again? I think it was 90. No, 99 or 98. Yeah, I think it was 98. Right. So you could have used your 98. Then it would be awesome. It will give you exactly the same thing, which is correct, because 9.9 is now rounded off. And now you can simply divide both sides, and you find that your kinetic frictional force will simply be 8.2 newtons. So yes, this is the first way in which you could have done it. Alternatively, you could have said the only force acting on this box as it is sliding from Q to R is the frictional force, which is a non-conservative force. Then you say it's equal to the change in potential energy plus the change in kinetic energy. But since it's moving on a horizontal track, then it means there is no change in height. And if the height is not changing, then the potential energy is not changing as well. So once again, the work done by the non-conservative force will be equal to the change in kinetic energy. And of course, your non-conservative force, you understand it's the frictional. So, yeah. So what is the conclusion we can make? Every time you are dealing with horizontal motion, don't use your work done by the non-conservative force. Use the work energy theorem. It works wonders in the. All right. Now, this is what they say. They say the barrier exerts an impulse of 14 Newton second to the left on the box when the box strikes the barrier. Now the question says, calculate the change in kinetic energy of the box after striking the barrier. Okay. So now one thing we know about impulse, what we learned about impulse is that it's exactly the same as the change in momentum. And one thing we know from the change in momentum is that we can actually find the change in velocity, right? Because what is going to happen here, the focus is no longer on what was happening before, like from Q to R. No, that's not the focus anymore. The focus is now on the box striking the barrier and the barrier exerting impulse on that box. So what do I mean by that? What I mean is this velocity of 4 meters per second, it is now the initial velocity in the context of impulse. Now, what we need to do is to find the final velocity given the change in momentum of this object. But let's try to show you a situation so that you can get it real quick, because we know and understand that impulse has to do with contact. There has to be contact between two things, right? So which is why we say here, this is going to be the change in momentum or whatever. Let's just say this is the velocity with which the box strikes the barrier. And maybe let's say this is our nice barrier here. So we know that when the box strikes it, it's going to exert a force on it, and the barrier as well will retaliate and exert an equal but oppositely directed force on this one, right? Now, this is the velocity with which the box strikes the barrier. It's 4 meters per second. Now, the final velocity is the velocity with which the box leaves from the barrier. What is the direction of the net force that is acting on the box? The net force is going to the left. The impulse is also going to the left, and the change in momentum is also going to the left. So now we need to decide on direction. Well, let's say anything that goes to the right is positive, which means anything that goes to the left is negative. Then we begin by stating the impulse momentum theorem. Now, what does it say? It says the impulse that is acting on an object is actually equal to the change in momentum. It's acceptable if you begin here, or you could have used it in terms of Newton's second law and say change in P over change in T. But it's nice if you state the impulse momentum theorem. So what? This entire thing, it's given to you as 14 Newton second. But then we just said the impulse is going to the left, or maybe we can expand it a little bit. Shall we do so? Yeah, maybe we can just say our F net change in T is actually equal to the mass times the change in velocity. That's how we defined the change in momentum back in term 1. Do you see that these topics are flowing together? Okay. So now we have negative 14 Newton second. The mass of this box is 2 kg. We are looking for the velocity with which the ball leaves the barrier, moves away from the barrier, not the ball, the box, I mean. And then we say the initial velocity is 4 meters per second because it's going to the right. Then here we get negative 7, which is equal to Vf minus 4. And so negative 7 plus 4, it's negative 3 meters per second. Okay, it's true. The velocity has to be negative because it's now going in the opposite direction, right? Okay. The question is looking for a change in kinetic energy. So now we can come and say, well, the change in kinetic energy is 1/2 m, the final velocity squared, minus the initial velocity squared. Now, this is the most important thing. Even though we can see that the final velocity is negative, you are not going to substitute negative 3 there. Why? Because in the formula for kinetic energy, we are dealing with speed and not velocity. So we only take the magnitude. So yes, and if we press this into the calculator, we find that the change in kinetic energy will simply be 7 joules, which is negative. And it makes sense that the change in kinetic energy is negative. Why? Because it tells us that this box has lost kinetic energy. It's true, because we said every time when we have two things that are colliding, then this was an inelastic collision, whereby the kinetic energy before won't be equal to the kinetic energy after. So you'll see it with a decrease in kinetic energy. Yeah, during that contact time, there was a loss of kinetic energy. Part of it was converted to sound because when it strikes the barrier, it makes a sound, and sound is a form of energy. And